Is that right? Thank you for the introduction. To the organizers for the opportunity. The title is Multilevel and Standard from Transformation to the my research is motivated by the equations that arise in geophysical fluid dynamics, and typical examples are the rotating shallow water equations and the stratified Multilevel equations, which are partial differential equations. But we also equations like a scale version of the Van der Poel equation. So these problems typically have many scales with both fast and slow modes, and this makes the time integration challenging. And for that reason, my research focuses on the development of efficient or fast time stepping schemes. And the first one I will present is a Parareal method with averaging into transformation. And the second I will talk about is a WKB-based time stepping scheme. Okay, so the issue with increasing the resolution. So in geophysical applications, one often wants to increase the spatial resolution to resolve the small scale structures, but this comes with a cost. So we often have to, or for many schemes, we have to satisfy constraints like the CFL condition to maintain stability. And this condition tells us that we have to, if we increase the spatial resolution, we also have to reduce or make the time step smaller. And this makes model runs longer. And this is where time parallelism comes into play. So we want to reduce the war clock time even when the model runs become longer. So this is the motivation for it. And throughout this talk, we will consider the following prototype problem: du by dt plus 1 over epsilon lu equals n of u. So we solve a time evolution problem for u. Epsilon is a small parameter. Then L is a skew-Hermitian linear operator. It has purely imaginary eigenvalues and is responsible for the temporal oscillations in the solution. Then we have a nonlinear operator N, which is quadratic for the case of the stratified Boussinesq equations and also for the rotating shallow water equations. And we can add a diffusive term D, which is not on the right-hand side. So, and due to the term 1 over epsilon Lu, the problem exhibits oscillatory stiffness. So as we want, so the solution has fast oscillations, and if we want to resolve the fast oscillations, we have to use small time steps. And this becomes prohibitive when we use very small epsilons. But the stiffness in the equation is not arbitrary, but we know that it comes from the linear term. So this allows us to construct tailored time stepping methods where we exploit analytical properties of the equation. Right, and one of such methods where we exploit the analytical properties of the equation is the multi-level Parareal method with averaging and the standards form transformation. I've worked on the problem in recent years together with Beth Wingate and Terry Hout in Exeter. And right, it is a time parallel method that we can use for our prototype equation. Before I dive into the details, let me place this in a broader context. There exist several multi-level methods for time parallel integration, including multigrid reduction in time, space, time, multigrid, and fast, which play an important role in the field. But today we will focus on the multi-level Parareal method with averaging and transformation in this talk. So this, as I've mentioned, this method is designed to solve oscillatory ODEs and PDEs, and it combines 3 different components. So the first is a Parareal method, is a parallel in time backbone. The second is an averaging technique, which we will need to handle the fast oscillation. The third is a transformation into standard form, which will also play an important role when we treat the oscillatory stiffness in the problem. Now, the first component, the transformation into standard form. So we have the linear term, which is 1 over epsilon term. And we can apply a transformation into the rotating frame, which has an exponential that depends on t, and applying the transformation yields a modulation equation, and this is the time evolution equation for W. So what we can see is that we do not have the nonlinear, the stiff nonlinear term in the modulation equation, but the expression L over epsilon t appears in the exponential. And in the exponential, this term is bounded and typically of order 1 in magnitude. And this indicates that we could eliminate the stiffness, the oscillatory stiffness with the transformation. And the modulation equation is still an exact representation of the problem. Right, and to further mitigate the oscillatory stiffness in the problem, we explore temporal averaging. So now the second component, what is temporal averaging? So the basic idea is we have a stiff problem with fast oscillations, and we replace it by a smoother problem. So the stiff problem is given here by the wiggly blue line, and we want to filter the fast oscillations by evaluating a convolution integral that contains f. So f is the function with the fast oscillations. And here eta is denoted as the averaging window. And as a rule of thumb, you can say that the averaging window should be at least as large as the periods that you want to mitigate. All right. Then rho is a kernel or a filter function. And rho controls the rating within the averaging window. So for example, you can emphasize values in the center and suppress values all the way. So here the figure on the right shows a typical kernel function, which is scaled for different averaging windows. And once we evaluate the integral, we get f bar. And in the figure, f bar is represented by the orange. We can apply the idea of temporal averaging to differential equations. So we assume that we are given a differential equation, dy by dt equals f of ty, and we have fast oscillations both in the solution and also on the right-hand side. So a typical scenario is that as we vary t, or f in the first component t, we have fast oscillations, and as we vary f in the second component, the solution is slowly varying. But anyway, as the right-hand side has fast oscillations, resolving the oscillations requires small time steps, which is expensive. Now, the idea is to apply temporal averaging to the right-hand side. So we replace our original problem, dy by dt, by dy bar equals f bar, and we get f bar from f by evaluating the filter integral that you could see on the last slide. So when we do this, we could filter the fast oscillations, and this allows using bigger time steps, and this will be the strategy how we construct the coarse propagator for the Parareal method. So I will later explain the Parareal method, but before I come to that method, let me explain the combination of the transformation with the averaging. And on this slide, you see results for the stratified Boussinesq equations, and in particular for the buoyancy component. So the black line is the time rate of change of the buoyancy. And for the red, green, and blue line, we applied the following procedure. So we took a solution of the stratified Boussinesq equations. We transformed it into standard form in the rotating frame. Then we applied averaging, an averaging method with different averaging windows, and then we use the inverse transformation. And what you can see is that the steep gradients are mitigated, and you mitigate them the more the larger you choose the averaging window. And this indicates that using averaging, well, as the steep gradients are mitigated, we can use larger time steps as we apply the averaging. Okay, now the two-level Parareal method, which we have seen. and yesterday. So the classical two-level parallel method is a method with two levels. We have a course level, which I will denote as level 1 in this talk. And the course level has a course time grid, and we have a fine level with several fine time grids and a small time step with validity. So on the course grid, we apply the course propagator, capital P, and on the fine level, we apply the fine propagator, little p. Right, and we compute the initial guess with a course propagator, big phi, and here n counts the time steps on the course level. Right, and as we have computed the initial guess, propagator takes the initial guess as the initial value, and the fine solutions are computed in parallel on the fine grid. Then we go back to the course grid, apply the course propagator again, and compute a parallel iteration, which is given by this linear combination here. And as we have computed the first parallel iteration, we can compute that one for the as a new initial guess and compute the second iteration and so on. So the parallel method is an iterative method. Right. And here n counts the number of course time steps and k counts the number of iterations. And as we've now know classical parallel method, we can combine the parallel method with averaging. And here, as well as on the following slides, I assume that our problem has been transformed into standard form. Right, so phi bar is a course propagator, and it solves an averaged modulation equation, and little phi solves the original problem. And with the original problem, I mean our time evolution problem transformed into standard form. Right, and at the iterate, we get a solution to the original problem. So first, we compute the initial guess with the course propagator phi bar, which solves the average version of the modulation equation. This provides the initial value for the fine propagators, which is again evaluated in parallel. Then we go back to the course level. We apply the course propagator again and compute a parallel iteration. Right. Okay, this is the idea of the two-level parallel method, which has been studied. And now the idea can be generalized to a multi-level scheme, and the idea of the multi-level scheme is recursive. So assume you want to solve a problem with L levels, then you have a course propagator and a fine propagator, and a fine propagator is a method with L minus 1 level. So now let's assume that we are given a problem with L levels. Again, we compute an initial guess. The course propagator solves an averaged modulation equation. And important to mention is that this time the averaging window is eta L, so it is indexed by the level. So we can choose a different average for each level, and only on the finest level we solve the unaveraged modulation equation. And the advantage is that we can adjust the time step on the different levels. Right. So then we have to decide if L equals 2. So if the number of levels is 2, then we have the two-level scheme, which I've explained on the last slide. And when L is larger 2, the fine propagator is a multi-level method of L minus 1 levels. So once the fine propagator is evaluated, we go back to the course level L and solve the averaged equation with averaging window eta L again and compute a parallel iteration, and also this whole process can be iterated. We can do a convergence analysis for the multi-level scheme. The foundations of the analysis of the multi-level scheme were analysis for two-level schemes, both with and without averaging. And in the two-level analysis, people made the assumption that the fine propagator is exact. So our first step was to generalize this result to the case where the fine propagator is not exact. And we combine this with the observation that the fine propagator of a method with L levels is a multi-level method with L minus 1 levels. And this then allows us to apply mathematical induction over the levels. And we get the error bounds that you can see here. So we have the delta 0, which is the time step on the finest level. Not the time step, which is the error that we make on the finest level. So it is just a time stepping error. Then we have the EL bar, which is the time step, which is the error we make on the coarser levels due to time stepping and also due to averaging. So it contains components for error components which come both from the time stepping and from the averaging. And we have the AJ bar, which are amplification factors, and these factors arise as we use fine solutions on to correct the solutions on the coarser levels. Now we come to the computational cost. So for the analyze the computational cost, we developed a simple model. First, let me introduce the coarsening factor, here denoted as capital N. And capital N relates the time step sizes between the levels. So we assume that we have on level L, we have a time step delta TL. And then on the next final level, L minus 1, we have a time step delta TL divided by N. So on the right hand side, you see a two-level method where the coarsening factor is 3. Now, when we count the time steps, we count the number of serial time steps, which is not the total number of time steps. So when you look again, in this figure, you see that we apply the force propagator in serial, but we can apply the fine propagator in parallel. So for example, we can compute the time steps which are in green at the same time, so they count as one serial time step. So, and as an example, assume that we have a problem that and we need x tilde time steps with a serial time stepper. When we have a two-level method where we do n time steps on the fine level, then on the coarse level, tilde over n time steps. And when we have a three-level method where we do n time steps on the fine level and n time steps on the intermediate level, we have x tilde over n squared time steps on the coarse level. So, and then we of course have to count the number of iterations that we do. Now, efficiency. So the idea is that we have constructed a multi-level method, and we want to know if the multi-level method has advantages over the two-level method. So we assume that we are given a multi-level method with a fixed number of time steps and also with a fixed number of iterations. And this multi-level method has a certain error, which is indicated by the dashed gray line here. And it also has a certain computational cost, which is denoted as complexity here, which is indicated by the other gray line. So, and then you want to construct a multi-level method, which is both more exact and is computationally cheaper than the two-level method that we use for comparison. Right, and if you construct the multi-level method smart enough, you can guarantee that the fine propagator of the multi-level method is more exact than the two-level method that you use for comparison. So as you do enough iterations, reach the accuracy of the two-level method with your multi-level scheme. Right, but as you do more and more iterations, also the computational cost increases. So the aim is to find a multi-level scheme where both the computational cost and the accuracy is better than that of the two-level scheme that we use for comparison. Right. And now we come to our first example, which is a very simple ODE. So it is an ordinary differential equation with two scales. Given by du by dt plus IRU plus u squared equals 0. So, and this ordinary differential equation is a simple problem of the weakly nonlinear system that we saw in the beginning. So in particular, I is our skew emission linear operator. R corresponds to 1 over epsilon, and U square is our nonlinear term. And with multi-level methods that we construct, we will resolve the fast oscillations on the finest scale. And one advantage of this example is that we can use an analytical solution, and we can use this analytical solution to check the accuracy of our numerical method. Right. So the problem can be transformed into standard form. So we get the modulation equation, and the modulation equation has the x of IRT term here. So in particular, this modulation equation is a non-autonomous system, whereas the original equation is an autonomous system. Right. And so the averaged equation is very similar to the modulation equation in the case of this ordinary differential equation. The only difference is that due to the averaging, we introduce such a damping factor, which is a complex number of small absolute value. So before we solve the solution numerically, we compare the solution in original coordinates and the solution in standard form. So in the original coordinates, we have oscillations and the amplitude, well, oscillations between -1 and 1. So the amplitude is relatively large. On the other hand, for the transformed problem, we have again oscillations, but the amplitude is between 0.0 and 1.1. And this indicates what we have expected previously in the beginning. We eliminate the stiff 1 over epsilon term, and therefore we reduce the stiffness. Okay. So in particular, the gradients in the right figure are less steep. And one important thing to mention is that here we have there's no error we have introduced no error because the modulation equation is still an exact representation of the problem. Now we come to the numerical solution. So the solid line with a relatively large amplitudes is the reference solution of the modulation equation. So this is a transformed solution. And the line with the dots represents the initial gas. For the initial gas, we apply the coarse propagator with the mitigated amplitudes, what we see here, right? And as we first could compute correction, the amplitude is correct, and also the phase is correct. And with the second and third Parareal iteration, the solution is even improved. So, and you can wonder why amplitude and phase is correct. So the correct amplitude cannot come from the coarse propagator, because from the coarse propagator, you only get solutions with mitigated amplitudes. And why do you have the correct phase? I mean, when you compute the first iteration, the fine propagator gets almost the same initial value. You just have very small variations. And for an autonomous system, that would mean you would get, for an autonomous system, you cannot expect the right phase. But as you remember, the modulation equation explicitly depends on t, so we have the x of IRT term, and you can conclude that this is where the correct phase comes from. Right. Numerical results for the case r equals 1000, or it is the same as 1 over or epsilon equals 10 to the minus 3. So we constructed methods averaging with 2, 3, and 4 levels. And the time step on the finest level is always 10 to the minus 4. We choose a coarsening factor of 10. And for example, if you consider the method with 3 levels, you have on the finest level, you have a time step 10 to the minus 4. On the intermediate level, you have 10 to the minus 3. And on the coarse level, you have 10 to the minus 2. And when you look into the table, you see that the error barely changes. So it's always roughly 2 times 10 to the minus 6. And well, as you increase the degree of parallelism when you use coarser levels, you can conclude that the multi-level methods are more efficient. And on the other hand, as increasing more and more levels doesn't change the error, you also can conclude that the error does not come from the coarse levels, but it must come from the finer levels and probably from the, or very likely from the finest level where we resolve the fast oscillations. The second test problem is the rotating shallow water equations. The rotating shallow water equations is a test problem that is often used in geophysical fluid dynamics, and it is valid when the horizontal scale is much larger than the vertical scale. We have equations for mass and momentum. So V1 and V2 is the horizontal velocity. H is the fluid thickness of the problem. So if we find two non-dimensional parameters, epsilon and f. Epsilon is a Rossby number, f is a Berger number, and we can add the fusion terms, which we in fact did when we solved the problem. Now, we solved the rotating shallow water equations for 2 and 3 level methods, 2 and 3 level Parareal methods with averaging. And by the way, the rotating shallow water equations admits the form of the weakly nonlinear problem that we discussed in the very beginning. Okay, so we use 2 and 3 level methods for the solution. We solve it for periodic boundary conditions. For the spatial discretization, we used 128 Fourier modes. The Rossby number was chosen as epsilon equals 1/10. We did tests for two different Berger numbers, 1/100. So in particular, we test the method for two different parameter regimes, and we added a hyperviscosity term with a coefficient 10 to the minus 4. On the left figure shows the initial conditions for the height, as the initial conditions for the velocity components were set constantly 0 everywhere. And I also included a figure which shows the height after some time. Now, the test of the method with 3 levels. So, shows a time step of 1/3000 on the finest level, and the time step from the of the intermediate and coarse level is depends on the fine time step and on the coarsening factors. Then, as you remember, the 3-level method has a coarse propagator, and the fine propagator is a 2-level method. And for this 2-level method, we did 3 iterations on the intermediate. We did 3 iterations, right? And we varied the number of iterations on the coarse level. And then for the 2 parameter regimes, we took a 2-level method, which we wanted to use for comparison. And for the 2-level method, we did just 2 iterations. So in particular, by using 3 iterations for the method, which is the fine propagator of the Parareal method, we could guarantee that the fine propagator is more exact than the 2-level methods that we use for comparison. And what you can see from the figures is that as you increase the number of iterations, the accuracy increases until the method converges to the accuracy of the fine propagator. Then this is more exact than the accuracy of the 2-level methods that we use for comparison. On the other hand, the computational grows as we increase the number of iterations on the coarse level. But it is possible to find a number of iterations where the 3-level method is both more accurate and computationally cheaper than the 2-level method that we use for comparison. I will come back to the Parareal method with averaging later in a summary. But before, I would like to talk about WKB-based time stepping schemes. So I've worked on WKB-based time stepping schemes previously together with Rupert Klein. And if you remember, in the previous method, we used a transformation into standard form. And here we use an alternative transformation, which is motivated by WKB approximations. As I've mentioned in the previous method, we use transformations into standard form with an exponential. And now we explore an alternative transformation, which is related to a WKB ansatz. Before I explain more details, let me just give you a brief overview about WKB solutions. So a WKB ansatz can be used to find approximations to ordinary and partial differential equations. And these are well suited for oscillatory problems because when you apply a WKB approximation, the solutions are represented as rapidly oscillating wave modes, which can have a nonlinear phase and a slowly varying amplitude. And the functions that describe the phase and the amplitude are slow to leading order. And so therefore they can be used for time integration. And now the question is this also a good coarse propagator for Parareal, which must be explored in the future. So the figure shows the idea for the of the method. So we have short time windows where we apply a time step delta little t. This time step is small. So with this time step, we resolve the fast oscillations. From the data that we get from the solutions in the small time windows, we extract the amplitude and phase information, and then we extrapolate the amplitude and phase forward in time using a big time step delta little t here at the beginning of the second short time. This is now, and one of the most important parts is the WKB ansatz, or the new transformations that is related to the WKB ansatz. So again, we have our weakly nonlinear system. So also this method is made for that weakly nonlinear system. And we define the corresponding linear system, which only has the linear term in the right-hand side. So we can find solutions to the linear system. So the I mu j are the eigenvalues, the rj's are the corresponding eigenvectors. And if we have zero eigenvalue, we have also R0 as a corresponding eigenvectors. And the Cj and C0 are the coefficients which are determined by the initial values. So, and when you have this representation, you can use polar variables to represent the coefficients and apply a variation of parameters ansatz, or a variation of constants ansatz. And this allows you to account for the nonlinear term, which appears in the original problem, the weakly nonlinear problem. So once you do this, you get this representation of the solution. So we have functions a0 of t and aj of t, which are functions that correspond to a phase. Then we have the cj of t, and the aj of t and cj of t are real valued functions depending on t. So in particular, we choose this ansatz such that we get a real valued solution when we have real valued initial data. Right. For simplicity, we will just write phi j for the function in the place later. And right. So, and this formula for YWKB is still an exact representation of the problem. So if we know AJ and CJ exactly, we could represent the solution exactly. And now one first example is the Van der Poel oscillator. And the Van der Poel oscillator is a second order ordinary differential equation. It can be rewritten as a first order system. And as we apply a scaling of the time coordinate, we also have we also recover our weakly nonlinear problem. So we have the linear operator and the nonlinear operator. The linear operator has eigenvalues plus minus I. We are given the nonlinear, we are given the corresponding eigenvectors, which are also normal, so they are normalized and orthogonal. we get our WKB representation of the solution, which corresponds to the formula on the last slide. Right, and for our numerical approximation, we have to find A of t and phi of t. And we can show that A of t and phi of t are slow to leading order. And this justifies why we can approximate of t and phi of t by a linear function. So we will, in particular, we will try to find the coefficients A0f, A1f, and V0f and V1. Now, this is a comparison of the van der Poel equations in original Cartesian coordinates and WKB coordinates. So for the Cartesian coordinates, we have y1 and y2, where the amplitude large. Cartesian coordinates, we see that the leading order is slow, and the slow leading order is superimposed by fast oscillations. So in particular, when we apply an asymptotic expansion of A and phi with in powers of epsilon, we see that the leading order is independent of epsilon, and the higher orders and the oscillations appear in the higher order. So in particular, the oscillations in A of t appear in order epsilon, and in phi of t, they appear in order epsilon squared. Now we also have a second test case, which is a problem with zero eigenvalues. And this is interesting in the context of geophysical fluid dynamics, because in the equations that have in geophysics, we often have Rossby waves and gravity waves. So the gravity wave modes are fast, but the Rossby waves are slow, and they correspond to the zero eigenvalues. So we have a system with three equations. So we have the linear operator, the nonlinear operator. The eigenvalues are given of the linear operator are plus and minus I, and additionally 0. And constructing a Lyapunov function, we can show that the point 0, 0, 0 is a stable fixed point. So we get a slightly different WKB representation. So we have again A of t and phi of t, and additionally we have A tilde of t, which we have to find right. So, and this representation makes sure that the YWKB of t is a real valued function. Now, how do we construct the time integrators using the WKB envelope? So as mentioned earlier, we compute simulations in short time windows. From that, we extract the information about A of t and phi of t. And then we use this data to find A-fit and phi-fit, which are, and as you remember, A-fit and phi-fit are just linear functions. And then this, with A-fit and phi-fit, propagates the solution forward in time, one big time step. And the construction of such numerical methods have similarities to Runge-Kutta. So a few more words about the fitting procedure. As you saw, the problem in the small time window, you compute 1 of ti and phi of ti. We find A of ti, so the amplitude function at the time points, by using this relation, and we can exploit that relation here when we compute the phi of ti. Right, and so once we have A of ti and phi of ti, we can solve a linear minimization problem to find the coefficients in A-fit and phi-fit. And one thing that is interesting to mention here is that as A-fit and phi-fit are linear functions, and we use it to make a big time step, A-fit and phi-fit ignore the fast oscillations. And so A-fit and phi-fit only account for the slow component in the variables, and therefore what we do is a type of averaging, which we will also see in the numerical simulation. But before I come to the numerical results, give me an outline of the numerical procedure. So first I show you the simplest possible method, and then I will show you two refinements of the method which can improve the accuracy. So first we solve the problem with a short time step datality in a short time window length L. And typically this time window must be chosen such that it covers only a few oscillations of the system. Then we use the data from that simulation to find A fit and phi fit, and A and phi in the WKB ansatz are replaced by A fit and phi fit. And this is a place where we introduce an error, right? So we replace the exact functions A of t and phi of t by A fit and phi fit. Right, and then we use the WKB approximation with A fit and phi fit to extrapolate the solution beyond the short time window. With one time step datality and get a new initial value at the beginning of the next short time window, where we can compute the next time step with the short time simulation. So right, so this method is it's an extrapolation method, and it has similarities to Euler's method. And we can try to refine the solution by constructing a method which has similarities to Hoyne's method. So this is so the blue part is different from the previous part. So again, we compute a short time simulation. In the first short time window, we find A fit and phi fit, extrapolate, and are at the beginning of the second short time window. And at the beginning of the second short time window, we compute another short time simulation with time step datality with length L. And we generate new data, and we use this new data to solve a new minimization problem and improve A fit and phi fit. And with this when we use this improved A fit and phi fit in the WKB ansatz, then we get a new time step. We get a new initial value for the next time step. So when we've done this, we can return to step one. And now we can iterate the process of computing improvements. So again, we first compute in the first short time window, we compute the short time simulations. Again, we compute again A fit and phi fit, extrapolate the solution, and are at the beginning of the second short time window. Now we introduce an iteration index k, and k to 0. And when k is already larger than an index value k max, k max, we return to the first. We get the extrapolation method or the Euler-like method, and we return to the final step. So when k is smaller than k max, we compute a correction in the second short time window. Yes, and we compute an improved initial value for the second short time window. We repeat this procedure as long as k is smaller k max. So here we said k plus 1. And once k is as large or larger than k max, we turn to step 1 to compute the next time step. Now we have applied this procedure to the Van der Poel oscillator. So we solved the Van der Poel equation for two parameters, epsilon. The first is epsilon equals 5 times 10 to the minus 3 divided by 2 pi. The other one is epsilon equals 5 times 10 to the minus 4 divided by 2 pi. The time step datality, which we apply for the short time simulations, is small enough to resolve the fast oscillations. Then we have two values for L, which is the length of the short time window, and L is chosen such that the linear system performs 20 oscillations. And we vary the number of course time step delta capital T. Right then. So the plot shows the results for the variations of the course time step. And I added two black lines. The first black line shows order 1 accuracy, so it has slope 1. The other black line slope 2. And what we can observe that the blue line, which shows the result for the Euler-like method, has roughly convergence order 1. The other two methods are converge faster in the beginning, but they reach a maximum accuracy. And they will reach a maximum accuracy, and after some time, with increasing time, the error slightly grows again. And this is very typical for problems that use averaging and averaging techniques. And what you can still observe is that the maximum accuracy that you can reach depends on epsilon. So in particular, it is roughly as large as epsilon. So this is the first problem. The second problem is a numerical test case where we had the 0 eigenvalues. So again, we have two different parameters of epsilon, 10 to the minus 3, 10 to the minus 4. The time steps on the short time window is again small enough to resolve the fast oscillations. Here we chose L such that the corresponding linear system performs 10 iterations. We again vary the number of course time steps. The blue line, which indicates the Euler-like methods, again has roughly convergence order 1. Then the orange line shows the Euler-like method with 1 iterations, and for the green line we computed more iterations. Again, the convergence is faster on the linear convergence in the beginning. Then we see the effect of averaging, and we also see that the error depends on the small parameter epsilon, so it is roughly as large as epsilon. Now I come to the summary of my talk. So my talk had two parts. The first one was a multi-level Parareal method with averaging, and the second part was the WKB-based methods. For the multi-level Parareal method with averaging, we showed or we explained that this is a version of the Parareal method which is specifically constructed to a weakly nonlinear problem. And this weakly nonlinear problem has as special cases the rotating shallow water equations and the stratified bussiness equations. We use a transformation into standard form and averaging to handle the oscillatory stiffness in the problem. We also discussed that a generalization of the two-level method to multi-level to multiple levels is possible. And we derived we explained the derivation of an error bound and interpreted the different terms that appear in the error bound. And where I showed numerical tests on one special ODE and one rotating shallow water equations, but more ODE tests can be found in a publication. Now, the second method is a WKB-based, or a method which was motivated by WKB approximations. One question is if this might also be a possible force propagator for the Parareal method. It uses an alternative transformation based on WKB approximations. The WKB approximations represent the slow dynamics, and in particular, we have approximations for the amplitude in the phase, function in the phase. And we performed first tests on oscillatory differential equations. So last but not least, a few open questions. So for the multi-level Parareal method with averaging and transformation, how can we construct multi-level Parareal methods with averaging for problems with many scales? So the most complicated problem we discussed is the rotating shallow water equations. Then is the performance of multi-level methods better for multi-scale problems? So is it worth to have a multi-scale method for Then how effective is the multi-level method for a broader range of physical realistic models? How does it perform compared to established methods? And how should we best choose the number of levels, sizes of time steps, averaging windows, and also the number of parameters? For the WKB-based methods, are the WKB-based methods efficient coarse propagators? Is the leading order independent of epsilon? We consider a problem where this was the case, and can we show that this is always the case for the type of problem that we are investigating, and if so, how we could exploit this? Then how can we account for oscillations in the higher orders? Does this improve the accuracy? So probably it would improve the accuracy because we suspect that the error that we saw is due to the that special type of averaging that we are using. And the third is how can we apply the methods to partial differential equations? This is a list of relevant literature. Work was published, and I will go back to the open questions. Thank you.
Yeah. Just a quick question. I didn't quite get the fitting in the WKB. Is this something you can do before, or do you have to redo this in every time step? Does this depend on the problem or also on the numerical parameters?
You do a computation for the time step, and from that you extract the information about the parameters. I don't know if I should go back.
You take the big time step again. Is that your question?
Yeah, but so you basically have to redo the fitting depending on your
Time step.
initial value. Or...
It's like getting the grade.
Yeah, okay.
But yes, that is true. But one interesting question is if it actually depends on epsilon, or if you could do independently of epsilon, because the leading order does not depend on epsilon. So that would be exciting. So in principle, the idea is that you solve it for any for the epsilon you like, that is the fastest, and you only extract the information that is independent of epsilon, and you can apply it for any epsilon.
That'd be nice.
Okay, these equations look like dissipation and dispersion. Is there any relationship between these equations and dispersion and dissipation? I don't know if you know about dispersion and dissipation.
Well, I can tell you that A of t is so for A of t you have to solve a dissipative problem. For phi of t you don't. I mean, it is a linear function with oscillations like.
It was related to my question, so thank you. One of the things that's interesting to me is the issue of aliasing. So as you look at your convolution to remove the high frequency, you pick up amplitude and dispersion errors for the phase. And I was wondering, what is the effect of your low order propagator? Because you're saying forward Euler or RK1 or RK2, right?
We use RK4. Yeah.
Oh, RK4.
Yes.
Apology. Because the dispersion and amplitude errors in the method would affect the aliasing onto a filtered coarse grid solution.
You had one? Yeah.
Can multi-level parareal and this averaging still be useful for systems where the transformation is not so clear, because I don't have a thing like this 1 over epsilon in the equation, but I still have multiple time scales in the system, oscillatory ones and so on.
I mean, the method was designed for this particular problem.
Yep.
And if you wanted to apply to a different transformation, to a different problem, you would have to derive a trend, or you would have to find a transformation which also mitigates the oscillations. Maybe this slide. So the trick is about using the transformations that you have large amplitudes, and with the transformation you get small amplitudes, and with the small amplitudes you reduce the averaging error. So When you can find a transformation of, I mean, when you have an oscillatory problem and you can find a transformation where you reduce the amplitudes, I think this should work.
I'll go back to you. You explained in this first averaging approach how the phase is corrected even though the coarse propagator doesn't have the correct phase. And you had a cartoon, you explained it, but I didn't understand it. Could you explain that again? So it's just after this slide, basically.
Right, but the observation is that the right hand side depends on t, so you have x to the IRT. And here you have the solution, you have the reference solution, and you have the mitigated solution.
So this initial guess is calculated by the coarse propagator, right?
That is correct, yes.
And so this has no correct phase information.
Well, it might be mitigated. It might be correct, but mitigated. I mean, the amplitude is not
Usually it
correct. The
gets the
phase could
phase.
be correct.
Yeah, usually it gets
So
the phase
coarse gets
correct.
the phase correct.
Yes,
Even though it's averaged out.
yes. In fact, that's kind of the whole game of this averaging, is to get the phase right and to let something like Parareal handle the amplitude.
So the course has the correct phase.
Yes.
Well, within an error,
Yes.
yes.
Actually, it is. Right.
This is something I would need in another node. It's called nodal integration method, and I can't do it. There's a different method for PDEs where you have a specific, it's like finite volumes, but it constructs the solution. I cannot get the phase correct. I have no way to get the, so here the course has the correct phase.
Yes, yes,
Can I
but
prove this?
there are, yes, but there are other mappings that can get the phase more accurate, such as Tim Andrews has found or works with a mapping that has a mean correction from the nonlinear term. Like if you assume the nonlinear term is constant, you can find a sort of implicit mapping that mops up additional phase error, for example. So, well, I don't know.
So if we look at the cartoon again, because you showed iterates of Parareal, right? So this is the first correction
This is the first correction.
that's done by the fine solve of Parareal, starting with the coarse approximation.
Right.
And how many time intervals did you have in this? So which are the time intervals of Parareal in this cartoon?
But
That was my question as well, which is I would love a little more insight on points per wavelength and Fourier content.
So this is the first iterate, and then if you do the second iterate now, and then you have a third iterate. And you go slowly back and forth so I can see it. Or we can look
I
at
hate to stop at this, but we're gonna have
So
a
I'd like to
talk
talk
on
about this later.
oscillations in
Okay.
just a second.
Okay.
The brunt of our question.
Yes. Yeah, so let's.
There will be again to talk.